Gesundheit. Gesundheit. So, electric force. This phenomena happens when two charged anythings. This can be, two electrons, two protons, or it can be two objects that have naturally accumulated charge. Whenever two charged objects are some distance apart, so we have up here two charged objects, Q1 for object 1, Q2 for object 2, some distance apart, there will be some electric force between them. And this is literally the force that either drives them to attract or repel. That force is determined by this formula. Electric force is equal to K. K is Coulomb's constant. This is a freebie. It's always this number. It's in your notes. K times Q1 times Q2. The Q's are the charge. In order for there to be an electric force between two objects, both objects need to be charged. And these are just the charges of both of them. So Q1 object 1, Q2 object 2. Each has their own charge measured in the unit of coulombs. And lastly, R is the distance between each object. But it's specifically the distance between the center of each object, because that's kind of where the charge is localized. So hypothetically, if I had two beach balls in one hand and the other, and they both were charged, the radius in that version of the equation would need to be the distance between the center of each beach ball, not the edge of each beach ball. Cool? Okay. And all these things combine to tell us what the force between the two objects in question should be. And like I said, this causes all of the rest of electricity to happen. So, to give a practical historical example, one of, if not the first forms of electricity ever recorded by humans is good old lightning. And I've labeled which arbitrary puffball is the cloud and which one is the tree, because the only difference between them in my art style is the presence of a trumpet. So, in nature, what tends to happen is you have a cloud in the sky minding its own business, but it gets stormy one day, and that cloud is joined by a bunch of other clouds. And I'm going to briefly discuss something that will come up a little more in detail later on. Have you ever wondered why rubbing your feet against the carpet or the wool blanket, or why the plastic playground equipment in your hair should cause charge to build up? The reason that this makes electric charges build up on one side or the other is because of friction. We blame everything on friction around here. Friction creates thermal energy, friction slows down machines, and friction causes charging, electrical charging. To back up just real briefly again. These two things are the smallest intervals of charge, meaning that if anything, like marker here, has usually most objects in the universe like to have the same number of each of these things, right? We're comfortable with that fact? If this marker had the same number of protons and electrons, what should its net charge be? 0. So the only way to cause this larger object to have a charge is to fundamentally change the number of one of those things inside of it. Typically that number is changed by moving electrons around, because again the protons are stuck. So what happens when you charge something by friction is the particles of one object physically collide with the particles of another object, And like how thermal energy will swap from one to the other, sometimes electrons jump from one to the other as well. And depending on what each object is made of, sometimes they get stuck after they've made that swap.
I think I read this somewhere that like when clouds, like during a thunderstorm, the clouds and then the surface of the earth act as heat, or not, capacitors maybe?
Sorry, repeat that.
The clouds and the surface of the earth act as capacitors, and then
Capacitors,
lighting
yes.
is the discharge of that charge switch, whatever.
Yes,
That like am I recalling that accurately?
you are. If you have a large solid wall of cloud floating above a large solid wall of earth, then if the clouds are negatively charged and the ground is neutral, that would form a capacitor, which we'll talk more in detail about in the coming weeks, because that's a specific part of a circuit that does a specific thing. But you are right. You're remembering correctly. And that does play a little bit into what happened next. So, objects rubbing against other objects can cause a charge to build up. Electrons will leave one of the objects and join the other, making the one that lost electrons positive and the one that lost electrons negative. So this one cloud has been hanging out with a bunch of other clouds, stealing their electrons over time. So now this one cloud is highly negatively charged if it's been using friction to just steal electrons from everything else. Those electrons don't want to be anywhere near each other, which is why sometimes when you look up in a storm, you see lightning arcing between clouds instead of coming straight down to the ground, because those electrons don't want to be in the same cloud, so they'll jump to a different one.
That's what it's the most scary.
Oopsie. You're not wrong, because if they're excited up there, it's going to be worse when they end up down here. So, this cloud, fully charged, drifting along. The particles in here don't want to be anywhere near each other, so they're looking for an opportunity to escape. Our formula, which I'm going to rewrite quickly, Fe equals K Q1 Q2 over R squared. Our formula tells us that this force is going to be stronger if the two different objects in question have a bigger charge and if they're closer together. Because if R is on the bottom and R gets bigger, the force drops. If they get farther apart, the force gets weaker. Meanwhile, if this number gets smaller, the force gets bigger. So there's more electric force between things that are highly charged and close together. So that cloud is drifting along, waiting for something positive and something tall to get close to it. Because the tip of this tree is the most positive thing nearby, and it's way closer than the ground is. So the cloud drifts and drifts and drifts, and the number of this formula just keeps going up and up and up until eventually that force gets so big, it is literally strong enough to take the electrons in that cloud and rip them out of the sky and into the tree. A lightning bolt is this force ripping electrons out of the sky. It can be. Now, fun fact, a fact, what you see here is not the electricity itself, because the electricity is electrons, which I have never seen one. I can't see a single electron. If you can, please tell me. So you don't actually see electricity. What you're seeing here is what the electricity is passing through. It's using the air as a conductor. Whenever you get a static shock by touching something, that light that you see is the air the electricity is traveling through. It's the same with the light bulbs. Electricity travels through the gas in the tube. The electricity leaves energy behind in whatever it travels through, And when gas has energy, it starts glowing at a certain point. So what you're seeing here is basically just spot welded plasma. It just ionizes and glows for a flash second as the current travels through it. Additional fun fact, if you could pause time and see this lightning bolt in progress, and if you could somehow, just take it and put it onto a scale, it would have a weight. Because the air has mass, and electrons technically have mass, which means you can weigh electricity.
Does it have more mass when it's glowing?
The gas itself, if you were looking at the weight of the gas would weigh slightly more when the electrons pass through it. It being hot doesn't necessarily make it weigh more, but it having electrons would, the moment that lasts. So, takeaways from this: lightning is scary, electric force drives all electricity, and all visible electricity is actually light given off by gas. It's not the electrons themselves. Yes.
Is that, is the R, lightning rods in there, John, problem?
I'm sorry.
Lightning rods, no little thing they, is the R part of it, that reason why?
Yes, the R is one reason why lightning rods are effective. To build a lightning rod that is designed to pull in lightning so that it doesn't shock other things, you want the rod to be high up so that the radius between the cloud and that rod is very small. You also want it to be positively charged, because most things tend to be neutrally charged. The lightning hits the neutral thing because it's more positive than a negative thing. Also, pointed objects tend to end up becoming net positively charged because of the way the electrons settle into the tip. So a pointy, positive metal thing very high up is more likely to get struck by lightning than anything else. So you, in general, in a lightning storm, want to be small, low to the ground, negatively charged, and not touching or near anything taller than you. So no golfing.
As a short king, I think I can answer that.
Yes.
Is it true you're not supposed to take a bath during a storm? Or is that?
That's in a, I can see where that came from, because most common water with things dissolved in it does conduct electricity, and metal pipes do conduct electricity. So if somehow lightning did strike the part of the water system or the lake that water draws from, sure, technically speaking, some electrons might worm their way into your shower head. But the massive caveat to that is electricity is very, very, very lazy. Which is why it only arcs into the tree once the cloud gets so close that this force becomes overwhelming. Electricity likes to go from the shortest path, from too many electrons to the most positive close thing possible. And so as soon as the electrons enter this tree, their next destination is the ground, because the earth beneath the tree is a huge neutral source that they can just dump into. And if, hypothetically, lightning did strike the lake or the reservoir that all the water comes from in Clinton, so body of water and the pipe that runs into the city, if lightning did strike this lake, electricity is now in the water. it's a lot easier for that electricity to simply transfer into the earth itself and dissipate than it is for it to worm its way through the water system and into your shower head. So, in general, the only way to really get deadly shocked is to touch the thing directly.
So just to show police our showers.
Well, I mean, I could see where the myth would have come from, because when these things were first being installed, everyone thinks, okay, water, okay, metal. We know those go zappy zap, so don't take a shower when there's zappy zap outside. I mean, I can see their train of thought, I just know better. So by and large, I would assume it to be completely safe. As long as, I mean, you're in more danger of something in your house electrifying your water than you're in danger of lightning striking the lake nearby and that hurting you.
And my electric kettle's really good at that.
Sorry?
My electric kettle is really good at that.
Okay. Wait, really good at shocking things?
And electrocuting the water. It heats it up, it boils.
Oh. I hope it's not literally electrocuting the water to do that. Most, not, sorry, my physics brain compels me to speak. Electric appliances designed to heat things use the electricity to produce thermal energy. They don't shock what they're trying to warm up directly. If you electrocuted the water, it would get hotter, but you'd most likely get sparks and an explosion of steam more so than hot water.
That's fine.
Professor Hoffmeyer, why are you trying to kill us?
Why would you put tinfoil in the microwave, does it?
That's because of radiation.
Also, Chick-fil-A biscuit wrappers are in fact made of metal. Don't
Yes,
put
I
them in
found
the
out the
microwave.
hard way. They're not entirely metal, but there's enough in there. Since you asked, the microwave literally blasts your food with radiation, but it's a type of radiation that only affects water and metal. So all food has water in it. You put food in the microwave, it gets hotter. It just absorbs the energy from the
If you
radiation.
put dehydrated food in the microwave, would it not heat up?
No, kind of like how if you put an empty ceramic mug in the microwave, it doesn't heat up.
So like if
That
you put
doesn't have water or
astronaut
metal.
food in your microwave, it would not heat up.
If there was absolutely no water in it, no.
Like straight out the vacuum seal package into the microwave.
If there was absolutely no water in it, it wouldn't heat up.
Oh, that's pretty cool. Now I want to.
You're not supposed to put,
Where are you getting astronaut food from?
You can't get it at the store.
okay, so what I would recommend you do is take your like a glass cup or a ceramic mug, fill that with water, put that in the microwave. Let it sit for like 30 seconds. You pull it back out. The water's hot because it absorbed energy from the radiation. The glass is bearable to touch because it's not made of water or metal. It didn't absorb heat from the radiation. It's only hot because it's touching hot water.
I'm still gonna try professional food, but maybe.
It would be harder for it to heat up in the microwave. I'm going to assume there's some water still in it, but it'd be harder for it to heat up. Metal goes kind of ballistic because it's conductive. So when metal heats up in the microwave, it gets hot and it loses its electrons. So it goes sparky, sparky, burn, burn.
Your adjectives today are just on point. I'm writing these down, so I remember.
Same thing happens with grapes.
Yes.
I used to have a whole notebook full of
Grapes,
things
grapes
I
and CDs also flip out in the microwave because of metals.
Wait, what did you just say?
Grapes. You
Grapes.
grab two grapes, you like put them together, like if you cut a grape in half, you put it next to each other.
What?
Don't well, it's crazy.
Wait. Did we learn this?
Why do you know this? Who
Watch
had
a
the
lot of
idea of
Discovery
putting
Channel
grapes in the
in the
microwave?
Have you seen the
Yeah.
thing where if you
I'm not
take
doing
a
it first.
spearmint lifesaver and draw it in your mouth and you shoot it really fast and spark?
No,
We did
I'm
do
worried.
in fourth grade as an experiment. You had to like dry out your mouth and suck out all your spit and breathe with your mouth open so your mouth got really dry, and it only works with the spearmint.
I don't want any of this to happen.
Lifesaver mints, and we turned the lights off and we all had them. We all had to chew like really violently, and everyone's mouths were sparking.
Yeah.
That sounds like a
I've
garage.
never had one in the classroom there because like the fridge is standing there not
So I
breathing.
have a few questions.
I think I'll pass on that experience.
It makes me laugh the person in for sent this email, Matt.
We will talk more about microwaves specifically at the end of the semester, since radiation is a type of wave. We're going to talk about the whole Earth spectrum here. So, I actually really enjoy these tangents. I really like this, but I need to make sure we use this formula at least once today because it's in the lab.
That's fine.
So, here's our first example. This is not actually a happy frog. This is two electrons that are 1 millimeter apart.
He does look at me.
I see it.
He's a little boxy.
It's not that funny, but it is cute.
I am bragging about that.
Sometimes the stuff that's not really funny gets the most laughs, especially when you're surrounded by other people that are chuckling at it. So these two electrons are 1 millimeter apart. These are going to be our two charged objects. First question is, what is the electrical force between them? What kind of numbers you guys got?
23 times 10 to the negative 28.
Barrett, we had 28.
I got the negative 42,
I don't know. I probably put something down.
but that might also be.
So, all right.
Oh, I didn't have milliliters converted.
That might do it. Yes. So all of our formulas are designed for meters. So 1 millimeter is 3.001 meters. That would then be squared. I will double check though, just to make absolutely certain. All the numbers that we have plugged in, just going to use our Coulomb's law formula. K is a freebie. It's always 8.99 times 10 to the positive 9. That's worth noting. It's a positive 9. The two Q's are the charge of a single electron each. And from our table at the start of this particular set of notes, all electrons have the same charge of negative 1.6 times 10 to the negative 19th. And distance between them, we can choose to ignore the radius of an electron because that's too small to count. So this is just the distance between the two objects. And I will double check. We'll work on that. Don't put in a negative number. Okay, so I got 2.3 times 10 to the negative 22nd. Does anyone disagree? Okay. So this is electrical force. It's still a force. It's measured in newtons. So this is a literal push and or pull acting on these objects. And a quirk of this formula, a quirk of this phenomenon, is that this force is acting on both objects with the same magnitude simultaneously. Now, just operating from two electrons, what direction are each of these going to be pushed in? Very good. Apart. Like charges repel from one another. So Q1 may push that way. Meanwhile, Q2, I know I'm going under the screen here, is being pushed the other way. So there is a little bit of, once you get this number, there's still a little bit of puzzling to it, because you have to look at the question and say, okay, so the object on the left is being pushed with this amount of force that way. Meanwhile, same amount of force here, but in the opposite direction. Yes?
So can't you just use force equals mass times acceleration?
Yes, you can. So looking ahead at the next question, what is the resulting acceleration of each electron? Electrons are particles with mass. So this teeny, teeny, tiny amount of force is going to act on their mass, which will create a resulting acceleration. And I don't remember this next number as well, so I'm going to tab back to the chart. Mass of an electron in units of kilograms. If you're used to grams, I apologize. This is in kilograms. 9.11 times 10 to the negative 31. So with that in mind, whoops. We calculated a very teeny tiny amount of force here. But what effect is that going to have on these electrons?
You're gonna move really fast.
They are. They didn't have a big number yet.
Yeah, it's really.
I would expect probably a times 10 to the 10th or a times 10 to the 9th.
Right.
Okay.
2.5 instead of 8.
And this is an acceleration, so that's going to be in meters per second squared. So, the sense of scale that I want you to take away from this. Most electric forces are going to be very, very small, because these forces are caused by single electrons and single protons, and there's just not going to be a whole lot of force from charges that tiny. You would never feel this. No human nervous system can detect something this small, which is why you tend not to feel the electrons in your body buzzing around. That said, tiny force on an even tinier mass can create pretty bonkers accelerations, which again, you wouldn't notice this. This would only last for the split moment these particles are 1 millimeter apart, because 1 nanosecond later, they're going to be blasted further apart, and both of these numbers will get even smaller. So this doesn't last long, but it does give some concept of how quickly the electrons move, even from tiny forces. Another sense of scale to keep in mind is that in nature, you will never find charges that are very big. This is 1 electron by itself. How many electrons do you think you would need all together in one place with no protons to have a net charge of -1 Coulomb? lot on the factor of like times 10 to the positive 18th or 19th, something that size, all by themselves. And the force it would take to get them there and keep them there, you could only ever see this in stars, and probably not even then. In nature, charges never get very big. All of the frizzy hair or static shocks you've ever dealt with come from very small charges, creating very small forces that are only significant because they're acting on things this small. If you somehow had a 1 Coulomb net charge, you might tear the universe apart doing it. Because it takes an extreme amount of force to get those things together, and the electric field it gives off would break everything. But I think that's a pretty good scale, getting a feel of the scale here. There's another couple of takeaways real quick though before we move past this specific example. How would this change if this second particle was a proton instead?
It would be.
Okay, very good, all at once. So I'll just go over all the things that I heard just now. If this was a plus, if this was a proton, then first thing that would change is that sign would be different. So instead of a negative times a negative, we'd have a negative times a positive, and we'd have a negative answer. So that swaps the sign of the answer. Additionally, colloquially, we know that likes repel and opposites attract. So in that parallel world where it was a proton instead, now they're being pulled towards each other with the same magnitude of force. So that is just to tell us, excuse me, if you get a positive answer out of this formula, they repel. If you get a negative answer out of this formula, they attract. You would also get a positive answer by putting in 2 protons. Positive times positive is positive.
So then does that make the acceleration really slow?
If they were protons, it would be slower because they have more mass. But protons are still really tiny, so it would still be like 2.5 times 10 to the 5th maybe. It'd still be really fast. But you're right, it would be slower. Any questions so far? Okay. I admit we didn't get it sort of like traditional halfway through break because we had a lot of questions and some low points in the middle and I got a little distracted. So I want to talk briefly about this before we go, but I'm going to take a quick breather because my vocal cord is tired and I need some water. want to touch on this very briefly before we break, because I do mention electric fields in the lab. So, I want to categorize them at least a little bit. This formula is the force that drives all electrical phenomena. Every single electrical thing happens because this force pushes things and makes it happen. This force comes from electric fields. So, the two charged particles that we have, protons and electrons, each give off electric fields. And these fields, these particles are functionally just radiating their electrical forces out in all directions. So protons create field vectors that point outwards from themselves. And electrons create field vectors that point into themselves. All protons are constantly just exuding this field out of themselves. And all electrons, they also have a field, but it points in the opposite direction, which is why you have the opposite charges. It's the same type of field, it's just pointing in a different direction. And this force, the electric force, comes from the fact that when electric fields overlap, when two objects that each have an electric field get near each other and their field lines begin to overlap, like if I continue drawing these out and these lines literally started to cross, that's when the force happens. Because when two fields of the same type overlap, you get a force between those fields and between the objects that created those fields. So the electric force comes from electric fields. And all charged particles are constantly exuding these fields. Protons out from themselves and electrons into themselves. And these field lines do end up bend so that they can flow coherently from positive to negative. So on screen right now, this is it is very hard to make these types of pictures. What scientists had to do was, this is a top-down picture of an oil bath filled with iron shavings. And they put vertically down into that oil bath an iron rod and ran electricity through it so that that rod was giving off an electric field. And the iron shavings in the oil fell into this shape along the field lines because the particles in the shavings are reacting to the field given off by the rod. And this picture is taken from above position, like so that you don't see the length of the rod. Excuse me. This is just one rod with the current flowing into the board. They took a second rod, put it over here, and had current flow in the opposite direction, thus creating like a negative electric field, like an electron. And the image that formed showed field lines bending from positive to negative. And when the field lines overlap and bend is when you get the electric force between the two objects. So the field lines were causing the iron shavings to bend along the field lines to match, and if those two iron bars weren't bolted in place, they would start drifting towards one another. Weird things start happening when you introduce multiple particles into the same area, or if their charges are the same. Positives and negatives attract because the field lines flow from one to the other naturally in nice flowing lines. Positives repel each other because positive fields don't flow into each other, they bend off of each other and don't want to be anywhere near one another. It's just uncomfortable. And you can see them visibly repelling here. They want to get further apart so that their field lines are more spaced out. They don't want to overlap. Negatives will ultimately do the same thing to each other as well. And this is both exactly the same as and the key difference between electric fields and gravitational fields. Does this formula look at all kind of familiar to you?
Yes,
Where does it look kind of familiar from?
it was all the impact.
Valid. You're not wrong. That said, it also kind of looks like this one.
Never.
Yeah, I was gonna say that.
Never would
Maybe
put that
that,
together.
right? With like the planets and stuff.
Right.
I got that
So
wrong.
this is the formula for the force of gravity between any two objects with mass. This is the formula for electric force between any two objects with charge. The formulas look the same and the fields work the same because they are the same. They're not like exactly the same thing. Gravity and electricity aren't the same force. They're cousins. There's literally 4 forces that hold the universe together. Gravity and the electromagnetic forces are 2 of them. And all 4 of the cousins work very similarly. The other 2 are the weak nuclear interaction and the strong nuclear interaction. So gravity works when masses give off gravitational fields, and when those field lines intersect and overlap, the 2 objects are drawn towards each other. Electric fields work when 2 charged objects give off electric fields, and when those fields interact, the 2 objects come together, or they repel. The math works very similarly. The formulas all take the same shape. Functionally, this is just what happens with masses, and this is just what happens with charges. The main difference is you only have positive mass. You can have positive or negative charge. Gravity can only point inwards. Electric forces can point in or out because of the duality. Same with magnets. The magnetic force is a little bit different. It's like Siamese twins with the electric force. So the 4 fundamental forces, the electromagnetic branch here has its own little subfamily of like sub-cousins that are themselves cousins with gravity and nuclear forces. This is just one of the electromagnetic interactions. But these fields are very hard to represent, which is why scientists have to go through the whole trouble of electrocuting an oil bath with iron shavings in it. And this is why we're doing simulators for the lab this week. Because I have no good way to show you this other than these photos and those simulators. So at least part of the lab is going to involve creating diagrams similarly to this by dropping protons and electrons onto a grid and seeing the field lines they make and how they interact with one another. The other part will be using Coulomb's law over there to calculate various forces between various things. And I'm taking up the full length of the class period talking today. So, the chapter 15 assignments will be going up very shortly. Do look over those. You'll also be looking over the lab this week. I will be in the lab room. I do recommend you come to work with your lab mates, and I'll be there to troubleshoot things. But it's a simulator. You don't have to. You can work together outside the room if you want to. Send me any questions you have about anything, and and do have a wonderful day.
Do you have printed copies of this, or do we go for it?
I will have some. I got in the building today at about 10 a.m., so I still need to make those.